So step 2 is look at the method development parameters. So first of all, we're going to select our column. And within column you have your surface chemistry, you've got your particle size, your porosity size, and the column length. So for the APC we have two main surface chemistries. We have the TMS bonded, the XT column range. They tend to be more suitable for organic soluble polymers. And we have the unbonded phase, which is known as the AQ. Tends to be more suitable for the aqueous soluble polymers. But either column chemistry can be used in any solvent due to the robustness of the APC particle itself. For particle sizes, you want the smaller particle size if you want high resolution, or moving to the larger particle size if you're looking at larger polymers where you want to either bring down the pressure or avoid any kind of possible degradation of the high molecular weight moieties. With the pore size, there's a variety of pore sizes available, and you will optimize this to your molecular weight distribution. We use individual pore sizes to maximize the resolution obtained, but this means if you have a broad polymer distribution, then you may need to make a bank of different pore sizes to cover the full molecular weight range. And of course you've got the column length. So we have 3 lengths of column to help you optimize depending whether you want to do throughput or resolution. So the columns themselves are actually shipped dry. This is for those of you that used to polymeric beds. If you let them go dry, then you know you've destroyed your column bed. But the APC particles are so robust, we actually ship them dry, and then you just flush them into any solvent that you require for your analysis. So here's an example of correct selection. So in the left-hand image, you can see where you haven't selected the full pore range. So the blue trace shows exclusion. So by adding another column, in this case the 450 angstrom, you push the molecular weight higher and you get the proper distribution as shown in the red trace. On the right-hand image, this is showing the effect of the column length. So the blue one is using the correct column bank, but only in 30 centimeter column lengths. So it's a very quick analysis, but you can see as you start to increase the column length, you get increased resolution, but at the cost of analysis time. And the optimum point of that is depending on where you're willing to compromise and what your analysis goals actually are. So we do have a very useful column selection tool for you to use, and this allows you to build up your column bank and your solvents before you set up your system to understand how it's going to perform. And this is empirically driven, and it's a very powerful tool. So to start with, you'd look at your target polymer, especially the molecular weight range. So this is 200 to 200,000 molecular weight polymer, centered around 20,000. So we'll look at what columns are available to us. So you have 5 different pore sizes here, going from 45 angstrom, very small, very high resolution column with a 1.7 micron particle size, going up all the way up to a 900 angstrom, 2.5 micron particle for the larger polymers, and that takes you up to 2 million molecular weight. So we'll go back to our column selector and we'll input a flow rate and select the first column as being the 450 to cover that full range of the polymer. And you'll see on the right hand side it's generated the calibration curve that you'd expect. We want to add another one to ensure that we have higher resolution down at that bottom end. So we add the 45 angstrom to give that real high resolution at that low molecular weight. And you can see we've on the calibration curve, you now have a kink in the calibration curve, and you don't really want kinks. You want that to be as linear as you can. So to cover that middle range, we're going to add another column in there, which will the 125 angstrom, which will smooth out that calibration curve, and that's giving you a really nice bank column set to perform this analysis on. As you can see, it will also give you the suggested columns, so you can see exactly what you need to purchase. Now looking at the method development parameters of solvent selection. So you have the solubility of your polymer, so what the polarity of your polymer and your solvent needs to be, the viscosity, any kind of additives you may need to ensure that you have true SEC behavior, and any other kind of system considerations. So for your solvent selection criteria, first one should be a fairly obvious one, is solubility. So you need a solvent that can entirely dissolve your polymer so you get real measurements. Some of these solvents can be very viscous when you're trying to dissolve polymers. What's the impact of this viscosity on the separation conditions? So the more viscous a solvent, the less efficient a separation's going to be. So how can you manage this? Additives. So you often need additives to ensure that you get true size exclusion behavior, i.e. no interactions between the polymer and the bed. Any kind of system considerations, so making sure that obviously the solvent's compatible with your system as well as your polymer. And it's worth re-emphasizing that solubility matters. You need the true measure of your sample. So in many cases you'll see that you either don't have a full solution, so you're either going to have to filter out some material which is actually part of your sample, or you're going to possibly put that into your system and maybe create a blockage. So looking at some of the viscosity values that you can have in with our solvent selections, you can go all the way from a very non-viscous solvent like acetone, all the way up to something that's extremely viscous like IPA. And so you can imagine, depending on where you are on the scale of this viscosity, you're going to have very, very different back pressures, and that's going to have a big impact on your speed because of the high back pressure, and also the efficiency of the separation itself. So what we can do is go back to our APC column selector tool, and at the moment it was in acetone at 20 degrees, and you can see you have a particular pressure of 6.7 thousand psi. So we can now change it to a different solvent. So THF is a very common solvent for polymer analysis, and you can see the pressure has changed, so it's now gone up to over 10,000. And also it should be noted that the elution volume on time is 6.8 minutes. So now what we're going to do is change the temperature to 40 degrees, and that allows us, because of the reduction in the pressure, allows us to push up the flow rate. So in this we changed two values, increase the temperature to 40 degrees and increase the flow rate to 1.2 mils per minute. And this gives us a operating pressure of the 13,000 psi, which is within the limits of the APC system, and it brings that run time down to 4.5 minutes. So it's a very powerful tool to work out your method or your column selection before you actually set up your system. So moving on to additives, why do you want to use them? So two primary reasons. One is the surface interactions. So with the APC column technology, they're not as inert as traditional polymeric beds. So you may find you need to use additives and modifiers on a lot of your systems. And all you're trying to do is prevent interactions between your analyte and the column bed itself. In terms of polymer chain interactions, then that's where you're actually trying to stop intermolecular interactions between the polymer chains. Again, so you have additives that prevent that happening, so that you're looking at the polymer in its native state, hopefully as an individual chain, as opposed to something like an agglomerate. So one of the neat tricks to trying to look at interactions is simply by changing the temperature. So in this example, because size exclusion is a temperature independent mechanism, by changing the temperature, it shouldn't have that much of an impact on the chromatography. So if you see a change, in this case changing from 30 to 50 degrees, you can see that there's a change in the chromatography. That's indicative that there's some absorption happening in your system. Of course, if you have a light scattering detector, that will also is a very good indicative way of looking for interactions. So what do? You need to adjust the eluent to eliminate the interactions. So we can add more, for example, more polar solvent or organic eluent. So methanol or water are common additives to THF. That will disrupt any kind of hydrophobic interactions occurring. You can add an acid or a base to reduce any kind of ion exchange interactions, or an ionic compound to the solvent. So it's very common to see lithium salts, for example, in organic solvents. And they're going to disrupt the intramolecular interactions or the agglomerates that we just mentioned. So there's a couple of examples. Here's a case of in 100% DCM, and we have our chromatogram. Already you can see that the traces aren't very well overlaid. This is indicative that something untoward is happening. But also we had expectations of what this molecular weight should be, and it was not as expected, and the PDI was very high. So in this case, I added a bit more of a polar solvent, so 5% methanol, and that brought the polymer distribution back to as expected, reduce those interactions. Similarly, here's a bisphenol A formaldehyde in THF, much lower averages than expected, as can be seen in the black trace. Again, add in a polar solvent, methanol again, we see the true size distribution as expected. You may have some kind of interactions with acidic polymers. So in this case, we added some acid to the mobile phase, and you can see again it brings the distribution to the expected distribution. Salts, so especially for something like highly polar solvents, DMF, DMSO, you may see agglomerates in your chromatography. So here in this red trace on the screen, you can see that you've got a very early eluting with multimodal peak. That's indicative of agglomeration. Add some lithium bromide at low levels, that'll break up those interactions and make sure that you're looking at the individual polymers, not the agglomeration. So there's a lot of different solvents that the APC supports, and then you can choose mixtures of these as long as they are miscible, and you can swap from any of these solvents to any of these other solvents on any of the APC column technologies. They're very robust and very flexible in terms of the solvents you can use on those systems. DMSO is limited support due to the addition of salt is required to bring down the freeze point, because when you're looking at high pressures on DMSO, you can freeze it. So you need to make sure you have salt in that system, and then you can use it as a normal mobile phase. If you want to use HFIP, that works well on the APC, as long as you replace the degasser with an appropriate one, which is, again, possible. We don't do high temperature GPC on the system, so we don't do things like TCB for polyolefins, for example. As we have this huge bank of solvents that you can use to really take advantage of it, we have this optional solvent select valve, and this enables you to very quickly switch between multiple different solvents. So we have up to 6 solvent lines available in the system, which allows you to screen multiple solvents, or allows you to change your column bank into different solvents, so you can use the same column bank to do multiple different polymer analysis in multiple different solvents. So it's a very powerful tool. Here's an example of one of them where we've swapped solvents. So to start with, we have a polymer in THF. We've analyzed the polymer, we've calibrated the system, and then we've switched from THF into toluene. We've analyzed a different polymer, Again, fully calibrated the system, swapped it into DMF, repeated with a different polymer, calibrated the system, and switched it back into THF and run the original polymer. On traditional polymeric beds, you may expect that this will either be a very long and laborious process, and you don't know whether during that process you're going to affect the column bed itself. But you can see the results on the bottom right, that the difference between the polymer in the original THF run, after going through all those multiple stages and back into THF, the results are essentially the same. And all this process can be done in a fraction of a time that you can do this in GPC. So in this particular one, I think it was done overnight as a practical way of running this. But also you may want to optimize your mobile face. So in this case, we tried different levels of modifier. So instead of just trying one modifier, seeing if it improves, we can change those different levels of modifiers to really achieve the optimal range. So here we've used the solvent switching valve to change different levels, and we've gone from 100% water to basically adding different levels of methanol, so 10% methanol, or choosing something like acetonitrile. And so this, including calibrations, has all been completed within 4 hours of the solvent of the system being switched on. So it's a very rapid way to screen solvents, but also to optimize your solvents for your particular polymer system.